I've had a pretty interesting career working in big data in one form or another. I'm really glad to see that everybody is here to talk about NoSQL. The reason why is because out of all the AWS services that we do, we recently did a marketing survey to find out that not many people know that we have DynamoDB. Well, that's a little disappointing because, you know, it's a little near and dear to my heart. So while most folks don't hear about DynamoDB nearly as much as some of our other services, we did find that the people that are using DynamoDB really like it. They like it so much, in fact, that we have very few customers that rotate off of DynamoDB. And the reason why has to do with how we manage NoSQL. How many today are managing a NoSQL solution of some flavor? Cassandra, Mongo, HBase, something. All right, so everybody is familiar with what NoSQL is, and we can skip over a whole lot of early explanation. So, how many of you guys are familiar with using a fully managed service from AWS? Raise your hands. All right, shout out what you're using. Shout louder. All of it? All right, okay, great. That's kind of the magic of what DynamoDB is. Managing a NoSQL database across multiple regions can be a bit hairy. It's very time-consuming, and people don't like doing it because it's not really as a differentiated task for your business as you would hope and the best use of your time. So what if Amazon could do that for you? What if we would manage your NoSQL solution so that you could have time back? That's what a number of our customers do. Customers, for instance, like AdRoll. AdRoll famously claims they spend more on snacks than they do on DynamoDB. That's a lot of snacks. I really want to see those snacks. Additionally, they only have like 1 or 2 DBAs managing that NoSQL database. AdRoll does ad tech. Its speed is of the essence, and what they deliver is a 40 millisecond round trip. So that's pretty difficult to do, and they're all building all of this on DynamoDB. So what DynamoDB enables you to do is focus more on other aspects of your business instead of managing a NoSQL database, and allows your business to be more agile, more scalable, all the stuff that we promise across the rest of the organization. And customers who have not adopted NoSQL and have a workload that warrant it kind of have a cautionary tale. Of the folks that are using some NoSQL permutation today, were you using a relational database for that workload before you moved over? So you have PTSD. I call it relational PTSD because I swear to gosh, if someone says, let's shard the database, I start shaking because it's just painful, right? I mean, nobody wants to refactor a database, from relational to non-relational, but man, nobody wants to shard a relational database either. That stuff is tough. So we had a number of customers in the past 2 years that, actually I should take a step back, probably in the last 4 years, but it's really taken off in the last 2 years where they start off with a relational database for a fast-moving project. Let's say it's IoT, and they get into a lot of trouble because it can't grow and respond and read and write fast enough. So DynamoDB is an excellent solution for those of us who are suffering from sharding PTSD. So with that, I'm going to hand it over to Nate. And he's going to come over and he's going to sort of make the transition from where we are from a relational standpoint to non-relational, and at the end give you an idea of how it incorporates directly into an application. Nate is one of our solution architects that has deep expertise on NoSQL solutions. And then after Nate speaks, Rick Houlihan is going to speak. Rick is a principal solution architect focused on NoSQL as well. And he's going to talk a little bit more about design patterns and best practices and where the gotchas are with DynamoDB. Because DynamoDB is just like any other NoSQL solution, that the devil is in the details. And wouldn't it be great if somebody gave you a heads up before you hit them head on?
What we're going to do today is we're actually going to walk through building a location-aware recommendation engine application, right? So rather than start with just sort of diving deep on the services, we're going to think about this like software engineers and really look at a set of requirements and characterize the data that we're going to be accessing, characterize our query patterns, and then pick an assortment of AWS services, and we're gonna talk about a lot of them today, a lot that come from our big data ecosystem, and actually build an application. At the end, I'm going to show you a working demo of an application that uses these services. This is the agenda. We're going to review some key concepts. Then we will review our application requirements. We're going to go through some data modeling, and this is to Rory's point about folks that are familiar with relational databases and entity relationship modeling. We're going to show how you can evolve from that into a NoSQL solution, right? So we'll actually take a look at some actual ER diagrams and what those look like in the NoSQL world. We'll talk a little bit about the data collection and storage. This is really represents the suite of services that we're going to use to build this, right? So this is going to cover not only DynamoDB, it's going to cover Kinesis, it's going to cover to the next point, machine learning, which you can use to actually analyze data that you're storing in Dynamo. And then finally, we'll go through a demo at the end. Let's talk first about what we mean by location awareness, okay? So we've all used a location-aware app. We use them all the time, right? Once people started carrying mobile devices around, we all have one of these devices, Basically, one of the great things about this is it knows where you are, right? It has a GPS in it, and so it can actually communicate geo-coordinates. And what that means is that application content can now actually be tailored to your location, right? And what you oftentimes do with this data is you may, if someone invokes a search or if someone's looking for some content, you're going to do your search and then filter it down based on the data that's most contextual based on your location. And so, with some of the examples of this, we have local shops or merchants or attractions, right? If you're walking around San Francisco and you search for burritos, it doesn't do a whole lot of good to show you burrito stands in San Jose, right? So you're going to want to search for those establishments that are close by. And then likewise with news and events, right? If you have an automated news feed, something along those lines, it probably makes sense to show you the news that's most relevant to you, right? Obviously, we do want to follow international news, we want to follow national news, but it's also nice to have some local news put in there. Anybody who's used social networking, and I'm sure most of us in this room have, you can also do some very interesting things with image and location, right? So if you take a picture, snap a photo with your friends at dinner, the photo app that you use on your phone will tag it with geo coordinates, and then you can begin to build applications that let you, do things like show you all the photos from your birthday in San Francisco, right? It can actually use location to show you the relevant content. So what do we mean by a recommendation engine? So a recommendation engine, similar to the location-based content, the recommendation engine is actually going to try and choose content that it feels like you will like or that you're going to respond well to. And we've all seen this, right? Advertising on the sides of websites or mobile apps tends to be based on information that is available in the cookie that is used to determine which ads to show you, right? But there's other sort of ways that you can use this, right? Again, going back to our restaurant example, if you're walking around San Francisco and it's 12 noon, hey, maybe show you a list of restaurants that are local to where you are, right? That would be an algorithmic way of generating a recommendation. And that's a very simple example, and you can do quite a lot of fancy things with algorithmic recommendations, but generally what happens is the logic, the if-else logic, as you start to analyze multiple attributes, gets really complex. And to solve that problem, you'll generally switch to something like a machine learning model, a predictive model. And so you can see in that second example there, here we're basically saying, if I get an input of a male who's between the ages of 18 to 25 with a food budget of $10 to $20, and he just searched for a restaurant called Taco Time, let's predict how well they're going to like that restaurant. In this case, we're saying the predicted class is 3 stars, and the probability of that prediction being accurate is almost 50%, right? So this is just an example of what you can do with these recommendation engines. So now that we know what location awareness is and recommendation engines are, let's talk about our app requirements. So we want to, obviously do searching based on location. So simple requirement, the user should be able to search for local businesses on their mobile device. And these are the terms, right? They would search by the name, by the address, by the description, and then by keywords, right? Keywords are just a random assortment of sort of key value pairs that we're going to ascribe to this data. And as we mentioned in the previous slide, we want those search results to actually be location aware. We're going to filter the results. So we're going to execute a query, and then we're going to filter the query results by location. And generally when you do this, there's a number of different ways you can do geo filtering. But one very common way, and one that's sort of simple to understand, is imagine drawing a rectangle on a map and then taking the diagonal of the rectangle. So in this case, we're going to take an XY coordinate from the top right and an XY coordinate from the bottom left. We draw a diagonal, and basically we're going to show all of the results that have geo coordinates within that rectangle. That's called polygon geo filtering. There's other sort of fancier things that you can do with circles and geo proximity, but for this, should work really well. For the recommendation piece, we want our recommendations to be based on a predictive model. So in other words, we're going to actually use application data that we're generating. As users are interacting with the application, we're going to store it, and then we're going to use that to train a model using machine learning. We want the user registration process to feel sort of non-intrusive. You know, nowadays, privacy tends to be a big concern. In fact, it's a little eerie sometimes with some of these digital marketing campaigns of how well they seem to be able to target you. So we don't want our users to feel like we're really asking them for lots of personal information. So we're going to keep it pretty simple. We're basically going to ask for their email address, their gender, their age group, and this will just be a grouping of ages, like a binning of ages, not a specific age or a birthday, and then a postal code. And in the real world, when you're doing machine learning, these may or may not have any correlation to what we're trying to do, but for the purposes of just demonstration and education, we can assume that we've done some analysis, and we know from our analysis that these tend to be correlated to the way users are going to respond to our campaigns. The recommendations are going to be offers from local merchants, right? So, users are walking around, they're searching our app, and we're going to promote some search results that have special offers from local merchants. And the last point here, this is really what's key to actually making the machine learning model work, which is we need to be able to track who clicks on the offer, and then possibly even if we can work something out with a vendor or we have some payment scheme through our app, how many of them actually convert on the offer, right? So it's one thing to click on it. It's another thing to actually, actually go in and buy the offer itself. But now let's get into data modeling, right? So just like any other application, we've got our requirements. We now need to essentially figure out what type of data are we going to store? What does that data look like? How does that data behave? One of the things that you're going to do, and this is, again, nothing new here, right? These are things that software engineers have been doing for decades. First thing is you want to characterize your data, right? You want to look at your data and decide, well, what type of data is it? So in our case, our location data, so these are the places that we're going to be displaying in the search results of our application. I think it's safe to say that it's structured, right? We saw with the search terms that we were going to have a name and we were going to have an address. We're going to have the geo coordinates. We're going to have some keywords. Arguably, you could say that's fairly structured data. It's mutable, right? It's going to change over time, right? If someone puts in a location, maybe the name changes. Maybe it goes out of business, right? So we're going to do updates on that data. And we have some one-to-many relationships, right? So we have this keywords where basically for any location we can have one or more, 0 or more keywords. Then we have the clickstream data, and this is a little different. So this is really semi-structured, right? It's going to be emitted as JSON. So there's some structure that's applied by the JSON, but it's likely not going to be fixed, right? Over time we may add attributes to the JSON, we may change attributes to the JSON. And the second point is really the more important of the two is it's immutable, right? It makes no sense to go back and update an event that already occurred, right? We're just doing an append-only operation here. It's basically we're just keeping a journaled log of these events. If this was 15 years ago, let's say, maybe even as recently as 10 years ago, software engineer, I used to be a software engineer in my past life, did a lot of this type of application development. I'd sit down and I'd build an ER model, right? I'd sit down and I'd say, okay, so here's my location data. I'm going to define an entity called a place. The place is going to have a primary key. It's going to have a name. It's going to have a description. We're going to have a type that may be like restaurant, store, wine store, something like that. Controlled vocabulary. So we're going to normalize that into a type table. We're going to have our keywords, right? So this is a one-to-many relationship between place and keyword. And so for each place, you can have 0 or more keywords. We're going to have our location. So this is where we're going to store the latitude and the longitude. And then off the location, we'll have the address, right? It makes sense to keep the address and location kind of in a set of related entities. a lot of different ways you can model this. I didn't intend this to be sort of the canonical way of doing this, but I think, in general, it's going to look something like this. And this works great, right? In the relational world, this will serve you pretty well. But let's take a look at this in a slightly different way. What if we looked at this instead of an ER model, but instead as a document model? So again, here we have some JSON. And you can see, we essentially have the same set of attributes that we're storing in our ER model. And we even have the same relationships, right? You can see that, keywords is an array. I can have, 0 or more of those, right? That's the one-to-many. We have the notion of a sub-object in a location that has the address and the geo-coordinate embedded in it. So, we're really representing the data in a similar way, but instead of using tables, we're using a document. What's the advantage of using a document model in our case here? Well, the ER model is normalized, which has some advantages. But the disadvantages are that you now have lots of tables that you need to join together in order to get your results. It's transactional, right? Every table has a key. You could conceivably do an update to all of the entities that comprise a place, right? You could update the place, the address, the location, and the keywords in a single transaction if you're using an RDBMS. Search, though, if we wanted to search on any potential attribute, we're going to basically end up indexing almost every column in every table. And in relational databases, that gets expensive, right? And then the fourth point is really significant. Over time, we may evolve our app. In fact, it's likely that we will, right? We may decide, we've modeled place pretty well, but it doesn't handle attractions very well. Like we also want to have, museums and zoos and other things that aren't really the same as like a merchant-based place. Well, now all of a sudden, we're faced with having to actually, change our schema, and that can be costly and expensive. In the document model, we're non-normalized, so we're going to have some data redundancy, right? We're not going to have the deduplication that you get from normalization. But we can add attributes without schema change. That's really a key point here, in that we can create a new type of place that has all or none of the attributes as other places. Maybe we keep the primary key and we keep the keywords, but we can make it completely different. And then the third point, and this is something we'll talk about when we go into the actual architecture of this, is using some of the technologies that we offer at AWS, you can actually very easily index the entire document and make it really searchable. And most importantly, you can make it searchable not only by keywords and text-based attributes, but also geo-coordinates, and that's exactly what we're going to do. Now that we know what our data is and how to characterize it, let's talk a little bit about data collection and storage. And here's where we're going to start talking about the actual AWS services. So when we look at our data, we've got transactional data, which is the typical OLTP type data. Can also be document-based, as we just saw. We have file data. Those are log files typically. They could be images. They could be other file-based. And then we have stream data, and you see stream data quite a bit with Internet of Things, as well as the clickstream data that we need to actually obtain in our app. And so if we look at that top line up there where we have our apps, we're going to build a mobile app, but it's going to talk to an app server and a web server, right? The way the mobile app architecture works is you usually have it, hit a bunch of API endpoints that you're hosting on web servers. And those are really going to be transactional systems, right? They're going to be reading and writing data from transactional databases like Amazon RDS and DynamoDB. Well, which one do we choose? Well, if we start with the RDS model and we use our ER diagram, that would work pretty well. There are some gaps in what you'll be able to query out of RDS directly, right? You would have to use a plugin like the PostGIS plugin to do geo queries, but you can do it, right? Works well. If we do DynamoDB, the document-based model works really well, so we can easily store our document in there. We also have a gap there, though, too, right? Dynamo does not have built-in geo-query support, but there are ways that we can combine Dynamo with other services to get that rich query capability. Why would you choose one over the other? Well, in this case, we're concerned with scale, right? We're hoping that our app goes from an install base of several thousand to several million, right? We're going to potentially have users all over the world. Scaling that on RDS is going to be tricky, right? It'll work up to a point, but eventually you're going to be running the biggest, fastest instance type, and there's just no place else you can go. And when that happens, you end up in this sort of means of needing to scale horizontally, which means sharding your database. That basically means putting subsets of data across different database instances. And if you're going to go horizontal scaling, I would argue you're in NoSQL territory, right? If horizontal scaling is what you need, then you really should look at NoSQL. So we're going to choose DynamoDB for this. It's also worth mentioning that immutable clickstream data is really, really great to store in Dynamo, right? You can basically do append-only operations into Dynamo. It's also going to scale really, really well, right? It can handle, however much write units you can throw at it, or write capacity you can throw at it. Let's now look at the entire ecosystem, because there's a few other services that we should consider for this. So on the left-hand side, you can see all of the sources of data, right? That's what we call data collection. So we've got the app servers and the web servers that we just talked about. We've got mobile devices, possibly IoT devices. We have log emitters, right? You have all kinds of log servers, syslogd and others that can basically stream log data all day long. And then you may even have some apps that are collecting data. And so if we look at how this works, you can see from the transactional side with Dynamo and RDS, we can basically use those as data sources for lots of different analytical tools, right? We could extract, transform, and load it into an MPP type system like Redshift or Presso. Those are data warehouses. Hive in some ways could also be considered a data warehouse, although it runs on top of the Hadoop framework. You can do Spark, which is basically an alternative to MapReduce that allows you to process data in parallel, batch processing. We have a service called Lambda. You can stream data into Lambda. We're going to talk a lot about Lambda today as we go through this. And then finally, for the stream data, right? Typically there, you're going to do streaming analysis, right? So you're going to do something like Spark streaming, Lambda, or a Kinesis client application, which is basically an application that uses a special library that has some features that make it easy to process data off a Kinesis stream. And so in our case, we're going to be dealing both with stream data. That's going to be our clickstream data, and we'll be using Kinesis to handle that. And we'll be using Redshift to basically analyze the clickstream results and as an input into machine learning. So Redshift is a very nice system for doing kind of ad hoc analysis, ad hoc queries. We're going to use that to basically sift through our clickstream data and then build our machine learning model. We're going to use DynamoDB to store everything else, right? And in fact, with Kinesis, one really nice feature of Kinesis is you get a multicast type of effect. We can actually have Kinesis send data to multiple places, and that's exactly what we're going to do here. Why transactional data storage for our app? Well, we need high throughput. It's going to be read, write, and update intensive, right? We're probably not going to do many updates, but we're definitely going to be doing reads and writes. And again, if this application takes off and we have an install base of 1 million different users, on different mobile devices, we could possibly have high concurrency. And then of course we need availability, speed, and recoverability. DynamoDB supports all of this. So again, we'll go into the details of how Dynamo works and how it stores data in the next presentation. But for the purposes of this discussion, just know that we can store our documents in there. We're going to be able to scale. We can get consistent latencies for reads and writes. Highly available, right? We copy data to 3 different availability zones within the region, and the API is simple and easy to use. One other feature that hasn't been mentioned yet that we will be using extensively to build this is something called DynamoDB Streams. So it's a relatively new feature, been out for 6 months or so, maybe a little longer. Really, really cool feature. This basically allows you to capture a change set from your Dynamo table. So if you enable this on your table, any insert or update of data in your table is going to be captured in the stream, and then you can process that. And you'll see, I think I have a slide coming up in the next slide or two. This really unlocks a couple of powerful architectural patterns that work really well. And this pattern will be how we solve the searching issue with Dynamo. Generally, what you'll do with streams is you're going to combine them with Lambda, right? So Lambda is a way of executing functions without having to run any compute. You just upload your code to us, and we run the function for you. We scale all the compute on the back end. You never actually have to touch an EC2 instance. And Lambda has various event sources, they're called, and DynamoDB streams are one of those event sources. So basically, you create the stream on the table, enable the stream, and then you write a Lambda function that's bound to the stream as an event source. And so every time there are events that are being put into the stream, the Lambda function is going to execute. And what we've seen customers doing more and more here is if you look at that middle DynamoDB NoSQL line there, you can see with DynamoDB streams and Lambda, I can do some very interesting things. I can basically materialize some of my Dynamo data into, say, Elasticache or to search. In this case, we're showing cloud search on the slide, but I'm actually going to use the Amazon Elasticsearch. And that's how we're basically going to, in this application, search our location data effectively, right? We're going to store it in Dynamo because we want the durability and the availability and just the concurrency and the scalability of Dynamo. But we're going to actually farm all the searching off to Cloud Search. And we're going to use DynamoDB streams and Lambda to do this. And I'm actually going to show a demo of how this works. Okay, let's talk a little bit about the event stream now. So we've got this clickstream data. This is sort of, again, this is important for our application, but it's not something the user is going to interact with. This is more for us. This is what we're really going to use to build our analytics. This is what we're going to use to do our really great machine learning predictive models. So Kinesis is perfect for that type of event stream. You can imagine, users are clicking around in the application. We want to capture all of that. We may want to do A/B testing, all the things that require, having to know what the user is doing, how they're interacting with the app. And Kinesis is well suited for this. So basically, all of your producers, essentially put data into a stream. We have authorization and authentication on the stream, so that's very nice. You can make this secure. Just as we do with Dynamo, we're actually going to copy the data in the stream to 3 different availability zones, so you have really good durability of your data and high availability of the Kinesis service. And then you can see on the end there, what's great is we can actually direct the data from that stream to lots of different places, right? We could put it into S3. We could do real-time dashboards if we wanted to. How much activity are we seeing on the app right now? Which offers are performing better than others, right? You might put the stream data back in Dynamo if you're doing that, for example. You can see the orange squares right beneath that. That's machine learning, right? You could actually send the Kinesis data to machine learning. Or you can send it to a data warehouse like Redshift or Hadoop. So what we're going to do here is we're not going to send the data directly to the machine learning service. You can't send it directly today. Machine learning takes a data source that has to be a file on S3 or a Redshift database. So what we're going to do is we're going to send the stream data to S3 and to Redshift. And then once it's in Redshift, we'll be able to create a data source that we can use to train a machine learning model. Kinesis Firehose. So this is a new service announced this past November or October at reInvent. And really what Kinesis Firehose does is it just makes working with Kinesis easier, right? Kinesis is actually pretty simple to work with on its own. But if you're dealing with a client application, you generally have to learn how to use the Kinesis client library. You have to run that code somewhere, probably on an EC2 instance. Lambda has helped, right? Running Lambda functions that respond to Kinesis streams is easier, in my opinion. You don't have all the compute to worry about, but you still have all that code to write. So what we've done with Firehose is we basically have created just some automatic or fully managed pipelines for getting data to S3 and Redshift using Kinesis under the hood. So you don't need to write any client library or Lambda functions, right? You just go into the console, you enable your stream, rather your Firehose. It's in the same console as a Kinesis console, and then you can tell it, send the output to S3, send it to Redshift, and you give it some information about which S3 bucket you want to go to, which Redshift cluster you want to go to. We scale it for you, so whether you have a trickle of data coming in and then a tidal wave, we'll handle all that for you. So again, splitting shards and all the things that you can do manually with Kinesis are handled automatically by Firehose. It's near real time, so we make best effort to get the data into S3 or Redshift within 60 seconds of hitting the stream. That's pretty fast, right? I mean, I think that means your data warehouse is probably just slightly eventually consistent. And most data warehouses are eventually consistent to the tune of sometimes 12 or 24 hours, right? You may load them once a day. And then, of course, as I mentioned, fully managed, you really don't have to do anything other than turn it on and then put data to the Firehose stream. What is machine learning? We hear a lot about it, self-driving cars. There's movies that come out that have all sorts of artificial intelligence-based themes and characters in them. And all of that, to some extent, is related to machine learning, but there are some important distinctions. Machine learning is really an offshoot of artificial intelligence, which is basically a broad computer science discipline that essentially studies how machines can learn, right? Off of machine learning, you do have things like robotics and computer vision. So those would be, some of the things you might see with like a self-driving car. And then on the right, or your left, we have knowledge discovery and data mining, and that's what we're going to use here. That's sort of the classic. You take it's a called supervised machine learning. You take a known data set and you run it through a number of different algorithms. You can do decision tree algorithms. You can do logistic regression. And then you get a model that comes out the other end. And you can use that model to make predictions. How does the model do this, right? How does it generalize your data? Well, an important concept is something known as segmentation. So you can see here, there's a very simple example. I've got a bunch of different colored circles. I've got green circles, I've got yellow circles, and I've got gray circles. And then we have the target variable, which in this case is yes or no. It's a binary variable. We just want to know, maybe we want to know, is this person going to respond to this ad that I serve them? How do you build a model around that? Well, in this case, we could say, well, let's see. It looks like green circles are always no. The yellow circles are yes and no, and the gray circles are yes and yes. So maybe we just split on color. Another way of looking at this, that's exactly what we do here. And you can see, okay, yeah, color works pretty well, right? For the gray, it's always yes. For the green, it's always no. And for the yellow, it's mixed. So we can call these pure selections, right? Meaning this is a leaf node in the tree, meaning every item in that node has the same value for the target variable. That's good. That's what you want, right? You want to try and find the attributes that give you this pure splitting. Well, this is a super simple example, right? What if we had 15 different attributes we were looking at? It becomes impossible to do this, manually. You need to use some mathematics and some algorithms to do it, and that's exactly what machine learning does. Another way to look at this is through a linear model, right? You could say, well, here's all my pluses and minuses, yes and nos, across these two different dimensions. Can I draw a line that segments one set of outcomes from the other? In this case, yeah, we can. We can draw it right here, and it basically gives us a pure data set here and an almost pure data set there. And this is the basis of logistic regression, which is the type of machine learning that Amazon Machine Learning does. I could probably spend the next 6 hours talking about machine learning. It's a deep topic, so we'll have to just sort of gloss over some of the details. But this is the underlying principle behind it, is you want to segment your data in a way that gives you the ability to take an unknown data point and categorize it into one of these nodes. Okay, so Amazon Machine Learning, easy to use, completely managed, right? Again, no compute that you need to run. You just basically prepare your data set and feed it into machine learning. We do a lot of recommendations on the Amazon site. I'm sure folks who've been shopping have seen that it tends to pick products that you'd be likely to buy. So a lot of this is based on our own experience doing this at scale. It can create models using data that's already stored in the cloud. In our case, we're going to use Redshift data. And then finally, once you have your model, you want to use it to make predictions. And so you can actually deploy those models in seconds and then make thousands and thousands of predictions in real time on the model. And again, you don't have to scale any of it. We do it for you. As a managed service, right, we've battle hardened this based on our own experience. It'll grow, right? You can start with a very small amount of data, and you can grow it to a very large amount of data where you're generating billions of predictions. What does a workflow look like? Well, you build and you train your model. Then you evaluate and optimize. And then once you've got a model that you feel is working well, you're going to use it to generate predictions. This looks really simple. I think anybody in the room who's been working with data science will tell you, it's really 1 and 2 are the hard part. First you need to understand your data. You need to understand which data is going to work best in a logistic regression type model. And then you're probably going to iterate on the model a little bit, right? You're going to run it. You're going to look to see how well it performs. The machine learning service has ways of evaluating your model. And if we have time during the demo, I can show you what that looks like for a multi-class model, which we're using here. And then once you've got a working model, you're going to use it to generate predictions. And this can be an ongoing process, right? A lot of times your model is going to get better the more data you have. And so I've seen a lot of customers, they'll nightly retrain their machine learning models and then push them out the next morning. Because it's a managed service and really there's not a lot of other stuff you need to run, you can very easily add it to an existing data flow. So you can imagine if we had an application that's writing out events to DynamoDB, we could see, hey, maybe our app is sending updates every minute with the new geo coordinates of the person who's walking around with their phone. We could say, oh, we just got an update of the geo coordinate. Let's actually do another prediction to see which offers this user is going to respond to, and you swap the ads out. You display a new set of offers. So really easy if you use Lambda with this to enable predictions. That's basically all the talking I have, and we'll jump into a demo now and look at some source code and actually see some working code, assuming everything is still working. I brought it up last night and it looked good, but with any live demo, things can change. This is our architecture, right? And you can see it's almost serverless. Aside from Redshift, which is the only piece of compute that we're running in our VPC, and Redshift is managed, right? You never have to log into the Redshift instances or anything like that, but you do need to lay out a network, put it in a VPC, create the database. Everything else is a managed service, right? All this sits in Amazon, the region that you're in, the AWS region, DynamoDB, Elasticsearch, S3, Kinesis Firehose, and Lambda. So pretty powerful stuff here. You can actually build really rich apps without having to run much compute at all. So let's now take a look at the demo. This is a mapping component, partner of ours. It makes a really nice JavaScript mapping component. Let's pretend that this is a mobile app, and this will actually work in a mobile phone browser. But probably we'd be doing a native app. And you can see when I loaded the page, it actually showed me some search results. Right? You can see these little pins on the page. What we did was we basically just took that top right and the bottom left. So we were able to compute what the geo coordinate was from the top right and the bottom left. And then that's what we use to filter the query results. And I'll move around in here and show you how things change as we go to different areas. How did we know to show San Francisco? Well, we got the geo coordinate and we basically centered it on San Francisco. So these are all just sort of common things that you do with location. You're basically going to say, well, where is the person? And now center that. You can either do basically a circle based where you basically center them in this circumference, or you can do a polygon based, and that's what we did. So if I click on let me actually do a search. Okay, fantastic. So it searched, and let's just make sure we really did get burger joints here. Yeah, umami burger. There we go. Okay. We have this machine learning. If I click on that, it will show you the rating for that restaurant. Unfortunately, I'm getting a cross-origin error when I click on that, but I will show you it to you from the back end. We'll actually run the prediction from the back end. So how did we do this, right? The data was in Dynamo, and yet I was able to search on a keyword of burgers and then get a geo-filtered query back. Well, so the real magic here is the DynamoDB via streams via Lambda to Elasticsearch. So let's actually look at that. Okay, so here's my Dynamo table. Can everybody see this? Let me actually make this a little bigger. So this is the notion of a place that we put into Dynamo. So and in this case, we're only storing restaurants. Again, for the example, I didn't want to create too much complexity. And you can see pretty similar to the document I showed earlier, right? We have the type of cuisine. In that case, that's our keywords. If I expand this. You can see in this case, it's a Malaysian restaurant. If we look at the location, I've got my address and I've got my geo coordinates. And so what we need to do, yikes, that's annoying. What we need to do is basically when we insert data into Dynamo, we need it to go into Elasticsearch, right? So let me do that. Let me actually put some data into Dynamo. not a whole lot to look at here, but what I'm doing is I have a JSON document, a big old JSON document that has a bunch of these restaurants in it. And I'm actually just using a simple Node.js program to read through that list of restaurants and insert them into DynamoDB. So as this is running, what's happening is that the restaurants are being inserted into Dynamo, and the DynamoDB stream is basically producing those items to the Lambda function, right? So I've inserted a bunch of restaurants. I have streams enabled on the table. Those items are being passed into a Lambda function, and then the Lambda function calls Elasticsearch and has it index the items. And we'll actually look at that code in a second. But first, let's see what's going on with Lambda. So what I'm doing now is I'm actually just going into the Lambda console. This is just the Lambda console, and we have monitoring over here. And you can see if I go to this link here, view logs in CloudWatch, this is going to show me the Lambda function execution. And it looks like, I think it's this guy right here. This is our stream. And again, let me just make this bigger. And you can kind of make out here, you can see here's my data that was passed in. And then I actually did using the Node.js SDK for Elasticsearch, I actually just did an index operation, right? What you do is you basically, and again, we'll look at the source code in a second, but it's real basic. I essentially just said, hey, here's my JSON, now index it. There's a little bit of magic you need to do under the hood to tell Elasticsearch which coordinates are actually geo-based, but that's relatively easy to do. You just set up what's called a mapping, which essentially defines the part of your document that has the coordinates in it. So you can see this is working, right? We have a whole bunch of events here that correspond to our data that we just loaded into Dynamo, and then via streams got to Elasticsearch. And you can see even here, here's the operation, right? This is the URL of my Elasticsearch server, and I'm basically doing a post, and this is the payload of it. Okay, so let's look at the code, right? Obviously, I work for AWS. Is this easy to do? Is this hard to do? Actually, really easy to do. Basically, when you write a Lambda function, and this is using Node.js, you can actually do this with Java, and you can do it with Python as well. But you create this handler function, and that's what passes in the data that you're going to, that's what hands you the data that you're going to process. And so in this case, I've got a couple of things that I'm doing where I'm getting some config information. This is where the searching would occur, right? So when I'm building my search query, I'm doing it right here. So when I typed in burgers at the top of the search box, that we're hitting this here. And you can see this filtering part right here is where I'm telling Elasticsearch, hey, I'm going to do a bounded box, and here's my top left and bottom right. Sometimes it's top right and bottom left. Sometimes it moves around, but in this case, we're doing top left and bottom right. And then we get the results back, and I just send back JSON directly to the client. And I'll show exactly how I invoke the Lambda function from the website. Let's look at the stream processing piece. So what's happening here is, in this case, I'm processing the stream data. And so the records are the collection of restaurants that I just uploaded into DynamoDB or inserted into Dynamo. And what I'm doing is I'm basically just taking the Dynamo wire format, it's called. If anybody here has worked with Dynamo, it's basically a key value format represented as JSON, but it has the data type embedded in it. And I'm just turning it to a regular old JSON. So numbers have this N type attached to it. Strings have an S. Lists have an L. Again, that's just a Dynamo wire format. All I'm doing is just creating a plain old JSON document, right? Actually, really, it's just a JavaScript object that gets serialized to JSON, and then I call the Elasticsearch index operation on the client, and I just pass in the body. That's the restaurant, and it takes care of everything else. And that's how we do the search. So how do we wire this all together, though, right? So I've got this Lambda function, all right? Well, this is firing a response to the streams, but what about the search, right? I have this web application that's actually needing to call Lambda. How do you do that? Well, let's take a look at that piece. So we have another service called API Gateway, which basically allows you to create public endpoints that are backed by code. And in this case, they're backed by Lambda functions. So my client application, in this case, it's a JavaScript web application that runs entirely out of S3. So it's all JavaScript. There's no server-side code at all in the website. It'll actually call these endpoints that I've exposed through API Gateway. And you can see these are REST endpoints, right? So for search, I basically have essentially a GET call that I've defined. And if we look at that, this is basically what it looks like. I have my integration. You can see my integration request is Lambda. So what that means is when the request comes in, I'm just going to hand it off to Lambda. And that was the code we just looked at. And then likewise, when Lambda's done, it's going to send the response back to the client. And API Gateway is a topic in and of itself, but basically I generate the JSON in the Lambda method, and I just pass it back out to the client. Let's actually just run this, right? So you can actually see this in action here. If I go to test. Oh, I'm sorry, I'm on the wrong one. Let's do restaurants. So in this case, I don't have any geo coordinates handy, but I'm just going to run with this one here. I click test, and you can see this is the JSON that comes back, and we've converted it. And again, you can do that very easily with API Gateway. And this basically is the format that the mapping component that I'm using needs in order to place items on the map. And so you can see I've got the name of the restaurant, the description. These are fixed, right? We decided to just use these colors, and then some information about the price and the restaurant. And we need why do we need these? Well, these are the things that we feed into machine learning, right? And I can actually show you a prediction. Let's do that right now. That restaurant is 1591. So let's actually do a prediction. What the machine learning model needs is it needs the restaurant that we're doing the prediction on, and then it needs the user ID. And it's from the user information where I look up the things like the age group, the budget preference, the gender, and those are what are fed into the machine learning model. And so what I'm doing now is I have this test user that I've set up in the system, and I'm gonna see how much would this guy like restaurant 1591 based on machine learning. Something happened here. Let's see what's going on. I must have put in a bad restaurant. Well, let's jump into, we can actually look at the machine learning itself right in the console. Let's take a look at how I built this model, because you'll see the, here we go. These are the inputs into our model. So age, budget, cuisine type, gender, price, that's the price of the restaurant, and then the rating. That's our target variable, right? And so what I did was I built a data set that had an even distribution of people of different ages, different budget preferences, different cuisines, different genders, and then given a restaurant, so if I pass in a restaurant ID, I can look up the how expensive that restaurant is. That's what price is, and then the model will predict, okay, how well does someone who's 35 to 50, who has a $20 to $40 budget, who likes Asian food, and who's male, gonna like a cheap $10 taco stand? What's that rating gonna be, right? And it'll predict it for me. And when you evaluate your model, you can look to see how well it performs. Let me pick, this one's probably a good one. For this particular case, we're doing what's called a multi-class prediction, meaning we have a sort of a set of values that we're going to get back. In this case, it's 1 star, 2 stars, 3 stars, 4 stars, or 5 stars, I think. Actually, it's not even that many. It's just 4. Dislike, satisfactory, good, and excellent. We turn those into stars. A binary model would just be yes or no. And then you have what's called a regression, which will basically give you an actual number. It'll predict a value. So in my case, I just wanted to predict this set of values. So the way that you evaluate the model is you take 70% or so of your data and you use that to train the model. You keep 30% aside to evaluate the model. You don't want to actually use all of the data to train the model, because what that means is when you go to evaluate the data, it may just be memorizing the data, right? It's just going to be predicting itself. So the diagonal here is the real value against the predicted value. And you can see for excellent, we're doing really, really well here, right? If we mouse over this, it's probably close to 100%. So yeah, 93% of the time when it predicted excellent, when we tested it using our evaluation data set, it actually was excellent. So that's good. When we go down here to very good, also pretty solid, right? We're at 91.18%. So, the darker these squares are, the better, right? If you see a nice dark diagonal here, it's okay. Satisfactory, not so much, right? So this one we're at 61.74%. Decent, better than a coin flip, but not by much. You can imagine if it's 50% or lower, you might as well just flip a coin to decide if someone's going to predict satisfactory or not. And you can see, if we look over here, it looks like we have some issues where satisfactories are being mixed with excellent. So for whatever reason, the model is predicting there. And then finally down here for dislike, we have 82%. So pretty good. So this is a decent model, right? Not great. There's definitely some optimization we can do here. And this is how you basically evaluate. So when I showed you that steps 1, 2, and 3, where you build your data set, you train your model, and then you evaluate your model, you're going to iterate on those steps, right? You're going to try and maybe I have to cleanse some data. Maybe I have some satisfactories that are outliers, right? Someone was having a bad day and they just said, they weren't going to give a good vote to anything, whereas lots of other people who share their same attributes would. These are a lot of things that go in, and for every machine learning use case, it's going to be different, right? I mean, I think there's a misconception with this type of stuff that you can just throw a bunch of math at it and it'll work. It's not true at all. You actually do need the math, absolutely. You need the software engineering to help make it work. But you also need the business sense, right? You need to understand who your customers are. What is your market? What's anecdotal? What's real? What's a signal and what's not a signal? So it's an iterative process. But machine learning makes it really easy. And these data sources, just bringing this back to our example application, these are, you can build these off text files in S3, or you can create them from Redshift. And I really like Redshift for this because, again, machine learning is one of these things where it's garbage in, garbage out. If you just throw data at it, you're not going to get a good model. But if you take your data and you query it and you look at it in Redshift, you filter it, you run some reports. I mean, a lot of data science is just plain old, running queries, looking at reports, looking at historical data, looking for patterns that you can then use to decide what's the optimal set of attributes that I want to use to train my machine learning model. You can basically then just write. What you do is you tell machine learning, here's the query I want you to run to get the data out of Redshift, and then it writes those out to a file in S3, and then it builds the data source off that file. And what's really nice about that as well is because it's tracking these, you can see how well your model's performing over time. As you create new data sets, as you build new models, you can always go back and compare and see what's changed. So I think I'm probably right on time here. So thanks so much. Hopefully you found it useful. I know we covered a lot of ground. In the next talk, we're going to go really, really deep into DynamoDB. And so you'll learn all of the details about what I kind of glossed over here. But hopefully you can see with the services that we have, you can build really, really powerful apps without really having to manage a lot of stuff.